Hey everyone, welcome back to the Physics 30 Unit 2 videos. In today's lesson, we're going to be looking at circular motion. So suppose you were riding your bike home after a rainfall and you drove through a puddle. When you get home, you notice that you have a bunch of mud on your back. So this is due to the properties of an object moving in circular motion. So as the wheel is rotating upward out of the puddle, excess water is flying off. And when it flies off, it's actually moving in a path that is tangent to the wheel. So when we're looking at a diagram right here, say we're spinning our wheels, we're riding on our bicycle, and this tire is moving forward. So what's happening is that some rain is going to, you go through a puddle, some water is going to be coming up, and it's going to be coming off of the bike. And so what you'll notice here is you have some water, if you're going at a fast enough speed, of course, it's going to be moving, and it's going to go basically be ejected straight off of this tire. And so this line here is called your tangent line, and really a tangent line is basically just a line that it intersects. Say if you look at a graph, say if maybe this wheel was a piece of a graph, but it's only intersecting at one point. That's essentially what a tangent line is. But anyway, so also looking at this, we can also see that this tangent line is also perpendicular with a line that if we were to connect the point where it intersects and the center of the wheel. So it's perpendicular, which, if you guys remember, creates a 90-degree angle. Alright, so when discussing speed and velocity, and this is in terms of uniform circular motion, there's a really important distinction that we need to make. So speed is a scalar quantity. If you guys remember what a scalar quantity is, that means it has just a magnitude, which is the size in the units. So in terms of uniform circular motion, speed is going to be a constant value. So velocity, on the other hand, is a vector quantity, which, if you guys remember, is the magnitude and a direction. So because it requires a direction, the velocity is continually changing as it moves about the circle, and because the velocity is changing, that means that it is also continually accelerating. So one thing that's going to be important here with velocity is that our size and the units are going to stay the same, so the magnitude doesn't change, but the direction does. And so if you guys remember back to what the definition of acceleration is that it's looking at a change in velocity over time. So our velocity is changing, yes, in terms of the direction, but it's still changing. So we have this continual acceleration of this object, despite only going maybe the same units and same size of, motion. Alright, so now we're going to talk about centripetal acceleration and force. So because the velocity is always changing, an object moving in a circle is accelerating. So we just talked about that one. Just drilling that into your brains there. So the velocity is constantly changing, meaning that we have some form of acceleration. The direction of the acceleration is inwards when we're moving in a circle. So it's moving towards the center of the circle or the curve. And since the change in velocity is pointing inward toward the center of the circle, the acceleration must also be going in that same direction as well. So this is called centripetal acceleration. And we can denote centripetal acceleration with your a value and a subscript c. And if you're working with, say, a vector quantity, we can always put an arrow over top of our acceleration variable, just to show we're dealing with a vector quantity. So if you guys just kind of want to know a little bit more about the meaning of the word centripetal, maybe this will help you understand or memorize what the word centripetal means. But centripetal in Greek means center seeking. So this is a type of acceleration that's seeking the center, so it's an inward moving acceleration. So anyways, so for an object to move with circular motion, it must experience centripetal acceleration. So it must experience some sort of inward acceleration. And if the circular motion is uniform, then so is the centripetal acceleration. All right, so according to Newton's second law of motion, if you guys remember Newton's second law, this one here is looking at the variable force is equal to your mass times your acceleration. And it was specifically really looking at how the different variables of your force and your mass will affect your acceleration. So if your mass is accelerating, then that means that it's experiencing some sort of non-zero net force. And so we can give this non-zero net force a fancy name called your centripetal force. And we can denote that with a capital F and a subscript C. So remember, centripetal meaning inward, so it's an inward force. And so one thing we do need to note here is that centripetal force is not the same thing as centrifugal force. If you've heard of that before, maybe you've heard it from some sort of sci-fi, Star Trek sort of show, or maybe you've just done some research on physics. But centrifugal force is actually the equal and opposite type of force to the centripetal force. So it's the equal and opposite reaction. And hopefully that rings some bells looking at Newton's third law. So if you guys remember, Newton's third law is that for every action there's an equal and opposite reaction. Okay? So the action is that there is a centripetal force happening, this inward force, and so the centrifugal force is going to be the opposite direction, but same in size. So if centripetal force is going inward, centrifugal force is pushing outward. Okay? And so really the centrifugal force that's pulling away, that's that tangent line that we were referring to in that bike example at the beginning. So many different forces could actually be the centripetal force. So for example, when a car turns a corner, the frictional force of the tires on the road acts as a centripetal force. If you spin an object around in a horizontal circle on a rope, the tension of the rope is the centripetal force. Another example, the force of gravity the sun exerts on the planets is another example of centripetal force. For an object spinning in a vertical circle on a rope, two forces, which is gravity and the tension from the rope, work together as the centripetal force at the top of the circle. And this is all because the centripetal force is that net force. So we're actually going to look at some examples later on in the next lessons, really kind of talking about this vertical and horizontal sort of circular motion. But first, we first need to talk about period and frequency of circular motion. So in many sports, desired skill is to be able to curve a ball. Say, for example, maybe you're looking at baseball. So a baseball pitcher can throw a baseball at speeds of about maybe 145 kilometers per hour, which is super amazingly fast. So with a flick of the wrist, the player can give the ball a spin, which does give it two types of velocities. There's a velocity as it's approaching the batter, and then there's that rotational or that circular velocity because of its spin. So the rotational velocity can be measured indirectly by measuring the time, which we call the period, capital T, it takes to complete one rotation. And another word for rotation could also be, say, a cycle or a revolution. And so one thing that's going to be really important here is the distinction between period and time. So the period we denote with a capital T, whereas, say, like a change in time or the time it takes for something maybe to move from point A to point B, would be a lowercase t. So period is the time it takes to complete one rotation. And so that really is only talking about that circular motion. Whereas we usually use the time in terms of maybe like a one-directional type of motion. And we're not looking at circular motion. So if an object is spinning quickly, the period may be a fraction of a second. So it may be very fast. So for example, if you were to examine maybe a hard drive on a computer is making a complete revolution in about 0.00833 of seconds. Like, that's really fast. So, and it's also kind of a hard concept to grasp, and it's kind of inconvenient. So sometimes what might be easier is to actually look at how many rotations you can do in a certain amount of time. So the period is one complete rotation, or how long it takes to do one complete rotation. But sometimes it might be easier to look at how many times can maybe, say, this hard drive spin, maybe within a second or within a minute. That might be a more useful bit of data, and it might even make a little bit more sense. All right. So I guess a different way to look at your period is the frequency. That one there we denote with a lowercase f. So this one here is kind of the opposite of your period. So rather than looking at how long it takes to do one cycle, now we're looking at how many cycles can fit in one certain amount of time, which we usually express as maybe like a second, and sometimes minutes or hours, just kind of depending on what we're looking at and how fast or slow the motion is. So the units for frequency are cycles per second. Or say if we were examining it in minutes or hours, you would just replace this part right here. And if we're looking at cycles per second specifically, then we have a name for this, which is called hertz. We denote that with a capital H and a lowercase z. Just make sure this is not a subscript. This is just a capital H and a lowercase z. So the units for period are cycles per second, which should make sense. Frequency and period are essentially the opposites of each other, or looking at the situation in, I guess, opposite terms. So frequency is cycles per second, and so your period is seconds per cycle. And so this does hint that the period and frequency are inversely related. So that means that if we had our period, that would be equal to 1 divided by your frequency. Or if, say if you're looking for your frequency, that'd be 1 divided by the period. So another common unit for frequency is revolutions per minute. We can denote this with RPM. So hopefully you guys have maybe heard of RPMs before. There's actually one of the gauges on your dashboard in, say, a vehicle will show the units as RPMs. And so your revolutions per minute, this is actually really easy to convert if you were given the units of hertz. And simply all you do is multiply or divide by 60, just depending on if you're trying to convert to or from your hertz. And that's just because, revolutions and cycles, that's essentially they're interchangeable terms. So that's fine. So you're just trying to convert the time is essentially all that's happening. And just remember there's 60 seconds in a minute. So you can either multiply or divide by 60. And if you're not sure which one, then just do your unit analysis where you create those fractions and then you try and eliminate the units from there. Alright, so I'm actually running out of time here on this video, so we are going to pick up the example and continue on with the rest of the lesson in the next video.